Alright, so inverse trig functions, which are just the inverse functions we learned earlier, applied to sinusoidal waves, or harmonic motion, I guess you could say, through physics. So a sine function looks something like this. Um, Let me just redraw it. So a sine function looks something like this, and here would be negative pi over 2. Here would be negative pi. Here would be 0. This is supposed to go through the axis or the origin, but I just can do it. And then this is pi over 2. That's pi, and that is 3 pi. Oh, or that one would be 3 pi over 2. So I did kind of draw it kind of wonky. But remember that there has to be a horizontal line test for our inverse function. The reason being is because if it hits two parts at the same altitude, I guess you could say, then the function doesn't know which input to give you back. So as a result, the people or the mathematicians of the past, I'm not exactly sure who, restricted the domain of the function to pi over 2 and negative pi over 2. This way, um, sorry. This way, pi over 2 would look something like this. This way, the trig function looks something like this. And notice that no values repeat. However, if you even move it slightly to pi over, like let's say pi over 1.9, then it will slightly cross over, repeating two values and not allowing for their horizontal line test. So they use logic to determine that between this interval there are no horizontal or vertical repeats of the function. So here they differentiate, or they figured out the trig function or an inverse function. And the reason why this is kind of hard to understand is because usually there is no algebraic expansion of sin x. You do get to Taylor series approximation later on in calculus 2 or 3. But here there is no real way to expand it out, and you pretty much have to use your calculator. Like I can only evaluate the angles, or I can only, in my head, if someone asks me what's the inverse sine of something like 42 degrees, it's going to be pretty hard for me to say what that is. So there's really no way to evaluate these things, which is why it's kind of tricky. So yeah. Um, so if the domain is x to pi over 2 and negative pi over 2, if you put this into the sine function, which is right here, we see that the range is between negative 1 and 1. So that means the inverse sine function has to switch the domain and range such that the domain is between 1 and negative 1, and the range is between negative pi over 2 and pi over 2. So that is just all an inverse sine function is. So let's get on to a practice problem here. So we have um, sine negative 1 of 1 half. I could do this pretty easily in my head. Essentially, this is asking if this is the evaluation of a sine function, what is the angle that makes this sine possible? So if you know your 30, 60, 90 right triangles, we know that the sine is opposite over hypotenuse. So this is 1 over 2, and the only one that is possible. Here's a special right triangle with 60 degrees. So that one's pretty simple. Um, so yeah, also be wary that sometimes, or for inverse trig functions, usually um, in higher level math, I think they use arcsine and arctangent. Um, and later on, there's just a lot of like trigonometric notation. But arcsine and inverse sine are pretty much the same thing. But don't get that confused with hyperbolic sine or hyperbolic trig functions. So let's take the derivative of sine x. And today I learned the formal proof of it because before I was using it a different way. So remember that since it's an inverse function, the inverse sine of sine x is just going to be equal to x for the domain that x is within negative pi over 2 or pi over 2. Yeah. Essentially, this will always give you the right angle, but only within an actual triangle. So essentially, on the unit circle, like let's say 7 pi over 2. 7 pi over 2 is right here. Um, but the angle made by the triangle is essentially 0 degrees, or actually it will be 90 degrees here. So it will return pi over 2 here, which doesn't give you back the 7 pi over 2, because that one just makes 3 laps around and then goes back over here. But it will give you the right angle for if you were actually going to put it in a triangle. However, this identity only holds true for this domain right here. So remember, we could just do sine on both sides. So it's going to be sine y equals x, differentiate or implicitly differentiate on both sides because we don't know what the derivative of y is with respect to x just yet. So it's going to be cosine y times dy dx equals 1. So then we divide it on both sides. Equals cosine y equals, oh sorry, I guess it would be 1. Dy over dx equals 1 over cosine x. So now we have to figure out what cosine x is going to be, or cosine y. But note that before we can just set this as an arbitrary angle y, and before we were told that we have x right here for the sine. So sine is going to be x, or opposite over hypotenuse, so it's going to be x over 1, such that sine of y is equal to x over 1. Then we know that this is going to be 1 minus x squared, and the cosine of y is therefore going to be 1 over adjacent over hypotenuse, which is square root 1 minus x squared. And we don't have to worry about the hypotenuse here because it's just divided by 1, which is essentially the same thing. So yeah, that's your sine function derivative there. So that one's pretty simple. So I'm gonna move on, and we get to cosine here. Same logic here. Let's draw the cosine out, and that cosine function looks something like this. So again, another simple wave here. So let's do the horizontal line test again. It fails. So my logic here is that you can choose an interval in which the values aren't repeated. So if you're watching this video, you can go ahead and take a guess, but I know what my guess is going to be. It's probably going to be this interval, or you can do this interval. But mathematicians are pretty smart, and they choose whichever one is, I guess, the most simple, although sometimes notation is kind of stupid. So I'm just going to choose an interval between pi and 0, because if we zoom in here and redraw that, it's just going to be this, and it does pass the horizontal line test. But if you spill a little bit over, so like let's say 1.1 pi, then it's going to look something like this, and it's going to fail line test. So again, we restrict the domain. Sorry, and we're going to go back here. So for the function cosine x, we have to limit the domain x is greater than pi or 0, such that no y values are repeated, such that when you take the inverse function and you swap the domain and range, and the range will be -1 and 1. I guess y negative, or 1 and -1. You can switch it so that the domain is going to be equal to 0 is greater, or x is greater than -1, 1, and the domain is greater than 0 or pi. So yeah, pretty simple stuff there. Now we just take the derivative, and the interesting thing about the derivative is that the derivative of the inverse cosine function is the same as a derivative of the negative of the derivative of the inverse sine function. So remember that the inverse sine function, or I guess y equals sine -1x, such that y prime is equal to 1 over 1 minus x squared. The cosine function is quite simple as well, such that y prime equals 1 divided by 1 minus x squared. So it's the same thing, except you just add a negative there. And I'll be doing the proof right here. It's the same exact proof here. So take an arbitrary right triangle, and the reason why we can choose any value here, I don't know. Oh, okay. Hold on. I'm just gonna. There we go. I don't know where that went. Okay, so the reason we can use any x value is because regardless of the ratio, the third side is going to maintain that ratio, if that makes sense. So, for example, if we take a triangle here, and we say that sine of theta is equal to x over 2, this can be x, this can be 1/2, such that opposite over hypotenuse is just going to be, or sorry, that can be 2, such that the sine of this angle is x over 2, or you can do x over 2 and make this 1, such that the opposite over hypotenuse is still the same value. So it doesn't matter there, just in case you want some math logic there. But since we're going to do the derivative of the cosine function, it's the same thing. So it's going to be y equals, let's just set an arbitrary function where y equals -1, or the inverse cosine x. So cosine y equals x, and then you implicitly differentiate, giving us sine y, or negative sine y, and I like to put the y prime out front, is equal to x, or actually is equal to 1, because we're differentiating this side with respect to x as well, and the derivative of x is just 1. So y prime is equal to 1 over negative sine x. And that triangle here, remember this is the angle, or this would be the evaluation of sine theta, or cosine theta in this case. So that's going to be equal to x1, so this is 1 minus x squared. And negative sine theta is going to be opposite over hypotenuse, which is just 1 over 1 minus x squared, with that negative just being right there. So pretty simple stuff. I feel like the difficulty of trigonometric math is that you kind of get into like logical issues, or not logical issues, but it's really hard to maintain logic. For me, that's the same with quadratic inequalities, because quadratic inequalities aren't linear inequalities, and there's no formal, like, it's like the same thing as domain and range. It's pretty hard for you to determine algebraically, because there is no formal way to do so. So that's why I guess cosine and negative sine is kind of hard, because they're geometric, and it's a little bit hard to evaluate. Like, as I mentioned before, like the inverse tangent of a specific angle, if it's not a special right triangle. So now tangent. Now I'm gonna leave this exercise to the reader, or to the viewer. So we'll take this is what the inverse, or what the tan function looks like. Notice it repeats every pi over pi intervals. So if you had to choose, where would you limit the domain? Well, any logical person would assume these two bounds, though you can do it here to here as well, or you can even do it here to here, but mathematicians again like to be quite simple. So that means we're going to restrict the domain of y equals tan x to negative pi over 2 and pi over 2. And notice that tan x has an unlimited range. The reason being, I guess we don't have to have a range. Y's I, R, or all real numbers. And the reason being is that sine x divided by cosine x, as it gets arbitrarily close to pi over 2, which is going to be, or sorry, if it gets arbitrarily close to pi over 2, it becomes sine, because remember that as we're really close to pi over 2, the height is essentially so many times larger than the x, such that this is a 1 divided by a very small number, and it shoots them to infinity. So yeah, that's why the domain is, or the range is unbounded for tan functions. So again, if we take the inverse tan of a function, all we do is we're going to flip the domain and range. So that means the range here, or the x, is going to be all real numbers. And the tangent function can, or the inverse tangent function can return a angle value between negative pi over 2 and pi over 2, which is pretty smart to me. That's pretty genius. And also, I like how the derivative of an inverse tan function comes out to an algebraic x value, as opposed to, like, for example, if you take the derivative of sine, it's cosine. But if you take the derivative of the inverse sine of x, you don't have any trigonometric functions at all, which I think is pretty interesting. So that's all about the trig functions. So if you want to pause the video, I will write the trig econometric functions here, or the inverse or the derivative of the inverses here. Um, so it's gonna be 1 over square root 1 minus x squared. The derivative of cosine x. Let me just do that. And I know my handwriting is pretty messy. It's gonna be negative 1 minus x squared, and tangent is the best one in my opinion. There's no square roots here, so that's pretty. Oh, actually, we didn't go over the tangent proof. But the logic remains the same. But I'll do so anyways because I want to be consistent. So, um, again, y equals 10x is the same thing as 10y equal or 10y equals x, such that we differentiate implicitly, which gives you a secant squared y times y prime for chain ruling it out with implicit differentiation equals 1. But note that secant squared y is the same thing as 1 over cosine squared y. So it's going to be cosine squared y equals 1 times on both sides. So it's going to be y equals cosine squared y. And we're going to draw out the triangle again. So note that the angle that produces that is just going to be opposite over adjacent, so x over 1, such that this is 1 squared plus x squared. And the cosine squared of y is going to be equal to adjacent over hypotenuse, which is 1 squared plus x squared. But obviously 1 squared is just 1. So yeah. The other functions are quite simple as well, or the other trigonometric functions, inverse trigonometric functions. They're pretty annoying to do because there's so many. So I'm just going to write them down. Though I'm sure the proof will be quite simple as well. The only thing I hate is how squares and square roots get really complicated, because your logic has to assume that the negatives or the inverse or the inner that the inner range isn't negative, because obviously squaring a square root does not give you the original thing back unless you restrict the domain past 0. So essentially, it's a lot of logic here, but just take the derivatives as you will, because the derivatives restrict the domain so heavily that you won't even have to worry about that. So 1 over x squared minus 1, and 1 over same thing here, except it's a negative. So yeah, that's all about inverse trigonometric functions, and yeah, it's pretty smart. So.